Okay, good afternoon everyone. Thank you for coming to the second undergraduate seminar series presentation for the semester. Our speaker today is Eduard Plint. He's a third year applied mathematics student, and the title of his presentation is How to Stay Hitched.
Hello everyone. So anyone who's known me for any length of time knows I'm quite fond of knots and knotting and all manner of things to do with rope and such. I eventually asked myself, okay, we've got all of these knots and stuff, and obviously different ones work better than other ones. So humans, we've been around for a hot minute, I would say, so I'm sure we've figured out something to do with knots. So I thought, okay, let's go and see what work has been done on knots, physical knots that is, and so forth. And I was honestly a little bit disappointed when I found that there isn't all that much solidified literature on it. So the first approach someone you'd take with trying to figure out what knot is better than another one would probably to do some empirical tests, work off of experience and so forth. And I had a paper here, but I've lent it out to someone. But this paper went through a whole lot of effort to compare the stability of different loops. But now let's say, okay, we want a bit more of a theoretically grounded interpretation of knots. So one of the things you can do these days is there's finite element and discrete element methods, which are quite good when you're not quite sure how things work, but you know the basic structure and you can break it down. So I've got two papers here, discrete element method, which essentially takes a rod and breaks it into little chains, and you can model using that, or discrete element method, where you just take the rope, triangulate it with all of your various things and tie it as you need it. But without giving myself and everyone here a crash course in those two things, I thought let's not go through that effort. So I found another attempt at modeling knots is you take a knot and you project it onto a 2D plane and you turn it into a directed graph and so forth, and you use feedback theory to model how the tension goes through the knot. But that requires a bit of crash course on feedback theory, and it's not as nice as I would have liked, so I'm not going to go with that one. So one model that I quite liked is Bayman's theory of hitches. So just to give an elaboration, with knots, there's obviously different types of knots. So the first one of the types of knots is a bend, which is to connect two ropes together, and now today we're going to talk about hitches, which is a knot that you use to connect a rope around another object. So we're going to talk about how to model hitches. So I'm going to pass this around so people can have a look at different hitches. I've got a clove hitch, a constrictor knot, a rolling hitch, and a boom hitch, so that if you just want to know the names as it goes around. And then I've tightened them all quite a bit so you can feel how tight they are, so we can have some grounding as to getting what you've got here. So now, obviously with a hitch, it goes around an object, right? So the way friction works when going around an object is we model it with something called a Capstan equation, which essentially explains the difference in tension depending on how many times you've gone around the pole. And that drop in tension is exponential depending on how far you've gone around it, as well as the coefficient of friction between the rope and the pole. So for example, if I take this rope, wrapping it around once will have less friction than wrapping it around, say, 3 times. However, just wrapping around a pole isn't going to completely describe how friction works in a knot, because otherwise I could just wrap it around and this would have the same behavior as a clove hitch, which, as I just showed, obviously doesn't happen. So there's another aspect within hitches that you have to take into account, and that is where the rope is pinched against the pole. Now this is quite difficult to model, which I'll talk more about at the end, but the way we're going to model it this time is we're going to say, okay, the difference in the tension on either side of a pinch is some magical number that is quite complicated to get, multiplied by the tension on top pinching the rope. So it's sort of intuitively you'd expect that the tension drop would be higher the higher the tension of the rope on top of the pinch is. So we're going to use these things. So just a notational thing, to make the working out all a bit easier, we're going to only consider full wraps around the pole. So this e to the mu theta thing is just going to turn into an epsilon to the n, where n is the number of times we've gone around the pole. And then, as I said, the eta is determined by the radius of the pole, radius of the rope, and just the general geometry of the knot. And it's an innocuous thing, but we're going to assume that this eta crossing number is the same for every single crossing in a hitch. I'll talk about that at the end as well. And then I'll talk about the delta later. So let's just talk about the clove hitch first. So I've got a nice drawing here, and I've preliminarily labeled all the various sections. So T0, the tension in the zero segment, obviously zero, or it's going to be some tension, but we don't really can say much about it. But now let's have a look at T1. The tension in this segment here. Using the pinching, we can see that it is dependent on this rope here, which is T2, as well as the tension in T0. So T1 is less than or equal to T0 plus eta T2. Everyone good with that one? So now let's move on to T2. Now T2 hasn't undergone any crossings, it's just gone around the rope once from T1. So we can see that it's simply that eta times T1. And now we come to T3. T3 hasn't undergone any crossings or whatever, so it's a continuation from Capstan equation from T2. And then we have T4, which gets crossed over by T2. So then we get T4 is less than or equal to T3 plus eta T2. Now we've got ourselves a system of inequalities, which I will spare doing in front of all of you now, because I can guarantee I will make a mistake. So after a bunch of work, we can arrive to a more usable inequality, which is T2 times some number, which we'll talk about now, is less than the associated tension in T0, the tail end. So now we've got two cases we need to consider. There is the high friction case and there's the low friction case. Now we want to see what values of eta and epsilon we can get to sort of guarantee that this knot or hitch will not slip. So let's first talk over the low friction case, because it's a bit easier to approach. So case one, the low friction. Now, when we have low friction, that means that our mu value, the mu, which is a coefficient of static friction, is relatively close to zero. So everyone, that makes sense, right? So what that then means is that the eta value will also have to be relatively close to zero, because eta is dependent on mu as well as a bunch of other things. And then because eta is close to mu, mu is close to zero, that means epsilon will have to be close to 1, because, so let me just notate it like this. So that just means we'll have to be close to 1, because we're exponentiating something, so e to the 0 will be 1. So that tells us that our epsilon 0, epsilon eta, will also be close to 0. And therefore we can conclude, just with this hand wavy sort of thing to get the feel of it, we can conclude that 1 minus eta is greater than 0. So what then that means is we can quite easily just divide by this without it affecting the inequality. So then we get the bound that T4, which is this tension, is less than a bunch of stuff, which I'm not going to rewrite, and after a bit more faffing around there, is less than or equal to T0. So now what does this tell us? It tells us that if the tension in the tail end of our hitch is 0, that means every subsequent tension in the hitch is also 0. So there's no tension in knot. which means that it must slip because there's nothing holding it together. So if the tension is low enough, that tells us a hitch will slip, which I think follows quite nicely from intuition. Everyone good with that one? So the high tension case is a bit nicer. We'll go over this a bit more rigorously in a little bit. Now the high tension case, we consider a high friction, Now we consider when mu is close to 1. Now we're not going to talk so much about eta because again eta is associated with mu and a bunch of other things. But if mu is close to 1, that means this, our epsilon, must be close to 2 pi mu. Just 2 pi. And that is a big number relatively speaking. So we can quite comfortably say that our n epsilon, eta epsilon, will be bigger than 1, which then tells us that 1 minus n epsilon, okay, I did my notes with a different epsilon here, so I keep writing it wrong, will be less than 0. But that means when we divide across by this inequality needs to switch around, right? So again, doing the same thing, that tells us our T4 will be some number is greater than some number times 0. Now, since we sort of assume that, I sort of tacitly assume that all the tensions are positive, doesn't matter what our tension is on the tail end, this will always hold because this number is negative. So this confirms the intuition that for a high friction case, doesn't matter what you're busy doing with this tail end, your hitch will hold. But now, I don't know about you, but this whole business about going with inequalities and trying to work with the system and doing this sort of hand-wavy thing doesn't quite do it for me. So just to put it quite casually, so there's a better way of going about this. Now, thankfully, Bayman has done a lot of the work for me. So I'm going to quickly just get rid of all of this. Now I'm going to do a magic trick. So, ta-da! So Bayman has gone about a way of taking all these properties and all of the things that you could go about for any type of knot and putting it into a nice matrix form. Now, just a small heads up, this paper was written in the 1970s. So the notation, I've done my best to try update it, but it's still a bit funky. And then also just the way that this whole model works is it cares a lot about the individual entries of a matrix because you're considering the individual crossings in a knot. So I couldn't find a neat way of rewriting it in our more modern notation. But let me quickly walk through all of the things he says we should do to construct a thing, and then I'll tell you which we do with these matrices in a bit. Now, first off, we're going to label each segment of the knot from the tail end up to the pulling end, and we're going to label according to where it crosses over each. So, as it says in point 1, that we label from where it starts underneath another crossing. So, the way we would update this then is we're going underneath something here. So this 1 is still fine, but we no longer need that 2 because there's no crossover there, and the 3 isn't necessary either because we're not crossed over. So this 2, this 4, because it's directly after a crossover, gets relabeled as a 2. Okay, everyone fine with how we're doing our naming numbering convention? So if I come to the more complicated constrictor knot, here's the first thing after a crossover, it's 1. We follow it, here's another crossover, so we label the next segment 2. We're going all the way around the back. Here's the next segment after a crossover, number 3. And finally, number 4. Everyone good? Okay, then we're going to have a number ni, which tells us the number of times that segment has gone around the pole. So for example, our segment 1 here has gone around the pole twice, right? And then we're going to, in accordance with that assumption over there, this doesn't go around, this goes around the pole 0 times, and then 2 goes around the pole twice again, and 3 doesn't go around the pole at all. Then the next number, the BI, is the segment under which the ith segment starts. So for example here, the 1 segment starts under 1, so B1 would be 1. But in this case, the B3 segment is 2, because 3 starts underneath 2. Okay? And then our last number, M, which is the number of times the BI segment goes around before crossing the ith segment, which it's a lot of words and you get used to it once you start counting. So for example, 3 would start after 1 turn of 2, but 1 starts after 2 turns of 2. I'll put up there's a nice table you can do to make all of these things work. And then what that sort of lets us do is generalize and combine those 2 equations into a iterative equation there, which I've tried my best with color coding, and then the I indices run from 0 up until the last one. He uses Q, whatever you want to denote the last entry by. And then, yeah, I'll talk about the summation in a little bit. Yeah. So now we've got all of these BIs and NIs and so on and so forth. So with these ones, we construct ourselves a lovely set of matrices. A, which is determined in terms of B and C, and then B and C is determined by a bunch of stuff. So the B matrix sort of captures all of the information about going around the pole. But the C matrix captures all of the crossover pinching effects of the pole. Okay, so everyone's still good with that one. So now let's sort of construct this for these 2, and then we'll talk about, once we've got these matrices, we can talk about when we can have holdfast conditions, and I'll talk about the interesting sum over there. So we start with I index, NI, BI, and MI. So now in this case we've got 1 and 2. So, but it will actually turn out that we don't use 2 because 2 is the tail end going off to being pulled. So we only have 1. Now 1 goes twice around our pole. And 1 obviously starts underneath itself. And it starts underneath itself after only 1 wrap around. So everyone understand how I get these? You look confused at the back. So we've got 1 segment only, 2 doesn't have any crossover effects. Now 1 goes around the pole twice. Now 1 also starts over here, underneath itself. But it only starts after going around the pole once. So that's how we get the 1, 2, 2, 1, 1. Okay? But now, because we've got only 1 entry, we get like a 1 by 1 matrix. So I'm going to just sort of emphasize that fact. And using that over there, so actually let's quickly do the B1. So B1 will just be 1. Let me just quickly specify. I did write it over here, but these funny things, the deltas, these are Kronecker deltas. So if the indices are the same number, it returns a 1, but if the indices are different numbers, it returns a 0. So just clarifying that for everyone. So B is 1 minus M1, which is, M1 is just 1. And then that's a 0. So we just get left with this. And C is 1 also times 1. So what this gives us in the end is B, which is 1, minus that, which is expression you should remember from when we did the whole inequality business. So, do you want to do the holdfast condition now, or do you guys want to first see how this works on a bigger system?
Show the holdfast so we know what we're doing.
Okay, so it will be. So, I'll do my best to give a explanation in a bit, but the way we find the holdfast is by taking the determinant of our A matrix and then equating it to 0. Okay, so the determinant of this A matrix is this that, so we'll equate it to 0, and then we solve for the eta, right? So in this case, eta is 1 over epsilon. So now what does this actually give us? So the way everything works out is that if you take your epsilon value, which is e to the 2 pi mu, you plug it in, and if it is larger than something we call a critical epsilon, so which in this case is, we want this to happen. If it's larger than our critical epsilon, that means our knot will hold. I'll define it now. Sorry.
Eta rather than epsilon. You were saying epsilon rather than.
Yeah. Well, okay. Everything is in E, so it's confusing me. Sorry. So we solve that. So if we plug in our numbers for whatever hitch we're doing, and it is greater than that, that means our hitch will hold. If it's less than, it won't hold. But I'll show a bit more this is just to plant the seed so you start digesting it, but I'll illustrate it a bit more after doing that example. Okay? So now this one is obviously a bit more involved because there's more going on. So let's do the I, this Ni, Bi, and Mi. So in this case we go up until 3. So there's 1, there's 2, there's 3, and 4 just goes off being pulled and doesn't contribute much to the knot. Now 1 doesn't, according to our assumptions, doesn't go around the pole at all. 2 goes around the pole twice. And then 3, like 1, doesn't go around the pole at all. Now 1 starts under the 2 segment. Can everyone see that? So 2 follows around here. So 1 starts under the 2 segment. 2 starts also under the 2 segment. And 3 starts under the 3 segment as well. And 1 starts after going, 2 goes twice around the pole. 2 starts under once around the pole, and then same for the 3 segment. So now we've got all these numbers. I'm going to steal some space from here. So first off, we're going to have our B matrix. Let me copy it down just to be safe. So I'm going to employ the much used tactic in situations like this and say, trust me. And so we've got those two, and then when we do the subtraction, so now when we take the determinant of that, we get this polynomial in epsilon. Okay, I'm not going to keep erasing it. If you bar epsilon and epsilon are the same thing in this situation. Sorry about that. And set it to 0. But we don't want to solve in terms of epsilon, we want to solve in terms of eta, because eta is the more complicated, messy value. So eta we solve as this. Okay, so but now we've got two expressions for different different epsilons in terms of friction and so forth. So a way of visualizing the significance of this is by plotting according to eta epsilons, right? So I'm going to sort of just differentiate the two. Let me do this. So the eta we got for the clove hitch was 1 over x. I'm going to draw it badly like that. But that epsilon times epsilon plus 1 will give something a bit steeper. So what we can see is that there's more space above the constrictor knots line than the clove hitches line, right? So that means the constrictor knot will hold for more values of epsilon and eta than the clove hitch. And I'm not sure where the stick has gone, but when you felt the constrictor knot should have hopefully felt a lot tighter than the clove hitch. So this so far confirms the physics. Thank you for the thumbs up. Thank you for the confirmation. So the constrictor, so this confirms roughly what we expect from our physical reality. But now we want to sort of confirm in general that this holds. And then I think in the explanation of this bit, it should become a bit more clear about what I mean with all of these etas, solving for eta and so forth. So let me just quickly clear up some space. I don't need this anymore. So the first thing we need to really think about is the shape that our B and C matrices are made of. So the way this progression goes is the shape of the B matrix is more important than anything. So let's first have a look at how the B matrix behaves. So again, a trust me moment, but if you want to, you can have figure out that yourself. But what we end up with that definition is 1s on the diagonal, 0s underneath the diagonal, the off diagonal above the 1s is got a whole lot of epsilonics going on, and then the remaining entries are all 0. Now I sort of confirm this by using SymPy, but you could probably do a bit more of a rigorous thing. The inverse of B has the form of 1s on the diagonal, everything underneath it is got epsilonics, and everything above is 0. So that is so this words. As my shirt says, words are hard sometimes. So this is important in how we go about determining. So our goal at the moment is now confirming that low friction case. The high friction case is quite messy, and I'm not going to go try to do that because it involves cofactors and polynomials and so forth, and I didn't feel like trying to keep track of all of that. So we're going to only talk about confirming the low friction case, which luckily only involves taking the derivative of matrices, but I've pushed all of that underneath the rug and just kept the important things for you. So we're going to consider the low friction case. Now, to go back, I mentioned a critical eta. So we're going to consider, we're going to say, okay, there is some eta where the determinant of A is greater than 0 when eta is less than the critical A, and the determinant of A is equal to 0 when eta is the critical number. Now, that greater than is somewhat arbitrary, but it will become clear as we go and why we say greater than. So we're only going to consider that top bit. Now, the first theorem that we're going to use is, I've labeled theorem 1. I actually broke apart his derivation a bit to make it a bit more manageable. First theorem, the elements of the inverse of A are all non-negative. So the intuition of this is we start with eta equals 0. So that means we only have our B. Okay? So that means we've got all of this. Well, ones are obviously non-negative, zeros are non-negative, and any exponentials all added together also non-negative. So you can sort of see the intuition behind how that works. Then our theorem 2, that's just for B inverse, but the inverse of A obviously is dependent on eta, right? So we do a bunch of taking derivatives, moving stuff around with matrix algebra, and we show that the derivative of A with respect to eta is non-negative. So that means the entries of A always increase. So that means they can never decrease from whatever B inverse is. So that means everything is non-negative. Does that track with everyone? That's just the intuition, but there's a lot more finickiness that is very difficult to get through. Then theorem 2, this basically amounts to saying that the left-hand corner is the largest entry of the matrix. That's essentially what it is. And then there's a whole lot of inequality business going on inside of there that we'll call on in a little bit. But now the sort of the punchline of this section is the theorem 3, which should look quite familiar to something we said a bit earlier. The tension in each segment of the knot is less than the tension in the tail end times the corresponding element in the inverse matrix. So if we talk about, say, the tension in segment 2, that means the tension it's less than T naught tension in the tail end times the first entry of the second row of the inverse matrix. So what this tells us is if this T naught is 0, that means every Tk must be less than or equal to 0. But since everything is non-negative, that means all of the tensions must be 0, so the knot slips. So let's go about proving this. Let me just clean up some space again. I will call on the theorems as we need them. So the way we got parameterized that system of equations we had at the beginning, that system of inequalities, is expressed in terms of this sum, and my way of writing it in a more modern context is saying, okay, the matrix A times the tension vector is element-wise less than the T naught, which is just zeros except for the last one, which is the tension in the tail end. So let me just put that there. I will just use some shorthand. So we've got that. Now by theorem 1, all of these things are non-negative and have non-negative entries. So that means we can multiply by the inverse without affecting any of the inequalities. Right? Everyone good with that one? Because the none of the elements of the inverse are negative. So the way you do it in the sum way, which after doing numerical it makes more sense, we'll do across K. Okay, I'm running out of chalk. Switcheroo time. So what all we've done now is multiplied both sides by the inverse of A. So in modern notation, it would look more like just doing this. Okay. Now it was just and doing some index stuff that you get comfortable with after a while. We get what we wanted, and then index stuff on that side as well. We get this, and then that delta just extracts the first column essentially. Now we showed by theorem 2 that all of these are simply less than the final thing. So we can calculate that one, and to sort of conclude the punchline, if that is 0, that means all of those are 0, so the knot slips. And then also as a how do you pronounce that? Corollary to all of the inequalities and so forth that happen in theorem 2, we also get sort of for free that all of the tensions are greater than 0, and the tensions going from the tail end to the pulling end increase. It's just a nice confirmation that there isn't any weirdness going on with all of the tensions. And like I said, this just follows from inequalities happening inside theorem 2 and 3. So yeah, okay, the determinant business. Okay, I forgot the determinant business comes in confirmation on the otherwise slipping thing. But you guys understood what I meant with the drawing of a graph with respect to the epsilon and eta, and then you calculate a number depending on your knot and put it on there, and if it's above the line it holds, if it's below the line it fails. But I mentioned in between everything that there's various problems with this whole model. So like the first problem is we assume only round terms, and obviously it doesn't go around completely, and depending on the size of your rope and pole and so forth, it goes less than and so forth. And then if that pole could make its way back to the front. The eta value, as I mentioned, we assumed that it's different for every crossing. But if I were to use the boom hitch, for example, you can see that there's a whole lot of business going on with all of the different types of crossings. So the tension is distributed differently over every crossing just because of the general geometry of the knot. So obviously that eta value will not be the same for every crossing, and that affects things. But luckily, these people, Modox and Keller, they have done a bit of continuum mechanics and so forth to get a nice bound. So if you ignore friction between the rope and itself, you can write, you just get the exact expression, you can write the eta in terms of the friction and a sine of some angle. Now this sine of an angle relates to this picture, but we've got a rope coming across here, where that sine is determined by the difference in radius between the pole and the rope, and I won't get too far into that. So it's that with a bit of extra work you can now redo those graphs. Instead of doing it in terms of epsilon and eta or mu and eta, you can now do it in terms of relative radius of your rope and pole. And because I was tired and I couldn't sleep one night, I eventually did do it. And what you get is a nice discontinuity at a certain point. So any radius below a certain point, or any friction below a certain point, doesn't matter the radius, your thing will slip. So to sort of exemplify this, these relatively thick, well, not really thick, but for the pole, these are quite thick. But over here, I have some very thin rope, and if I try and tie a clove hitch over here, just flips off. Poor choice of words. And if I try to do a constrictor knot, it holds a little bit better, but it will highlight another assumption we've sort of made about, come on, behave yourself. It will highlight another assumption we've made about our pole. So that holds better, but you see how it's being pulled away from the pole. So we assumed sort of tacitly that the geometry of the knot is unchanged as we apply tension to it. So that would also, this sort of highlights that assumption. And then of course there's certain knots that perform better at different angles of pulling. So for example over here with the rolling hitch, a rolling hitch is designed to be pulled in this direction. You can see it's not going anywhere. But if I were to try and do it with a different one, it would eventually slip a bit more. So this model also just assumes uniform tension that doesn't break anything, and with no funny angles. And then a nice interesting thing that it does highlight is the holdfast condition we got for the constrictor knot is precisely the same as that for the rolling hitch. So that tells us that sort of highlights the intrinsic geometry of a constrictor knot is better than other things because it only goes around the pole twice, but the rolling hitch goes around 3 times. So it sort of gives you these nice little highlights. And then the boom hitch is a big mess. It's got a lot of stuff going on in it. So yeah, that's a basic model you can use to model hitches. So any questions?